Today we'll be discussing how to solve incompressible fluid motion coupled with mass continuity. And the method that will be used is the projection method from Chorin 1961, which is based on Helmholtz-Hodge decomposition. At the very end, I will explain the motivation or the proof behind projection method and how it's essentially the same thing as Helmholtz-Hodge decomposition. So, normally when we solve the equations for the atmosphere, we're compressible. So we have here's just a basic form of the atmospheric equations. Just for simplicity, this process would be the same if we had all the terms. But these are our two terms. This is our x direction equation for x velocity, and this is our equation for y velocity. And just wanted to note that this is inverse density, so the amount of volume per mass. And for the atmosphere, it's compressible, so this is our equation. It's the change in density over time is essentially equal to how much density is being fluxed into this region. So it's a flux convergence of density, which makes sense. Density increases if density flux converges into a region. And it's called flux because the rho is on the inside here. I won't write this out. This is missing some terms. This here should have rho u, rho v like this. Right. So the way to solve this is step one, you solve these two equations individually for the next time step u, next time step v, and we're compressible, everything's fine. But now we need to update this term. So just note that this is inverse of this. So they're essentially the same thing. You solve equation 3 here for density, and that would just be, if you want alpha, it's equal to 1 over rho, right? So I'll just write that. Alpha is equal to 1 over rho. And to update pressure, you would need to use like the equation of state and thermodynamics, which is this one, equation of state and thermodynamics here, to update pressure. And now you can we can restart the process. So once you do this, you can go back to step 1. But what if the fluid is incompressible? So this is our equation we just had for the mass continuity. Basically, mass is neither created nor destroyed. But in an incompressible fluid, rho pretty much stays the same. It's very, very constant. So if you look at a single location, the density is pretty much going to stay the same. So if any air leaves, or water in this case, if any water leaves, new water will come into a place immediately, and density will not change at all. So this, if you say rho is constant, that's the same thing as saying the time derivative is 0. It doesn't change over time. And so you get rid of this term, so we just simply have this term, which we said rho is constant. We can take rho out, equals this, and then we can divide rho by 0, or 0 divided by rho goes away. We're simply left with this equation. The divergence is 0. So like I said, you can't have a situation like this. If air goes this way, air must come this way, if it's incompressible air. But obviously air is not incompressible, so sorry, again, I should be talking about water. So the issue is momentum equations, these equations, they don't conserve mass on their own. You have to update density, that kind of thing, as we just saw. So now we need to solve this equation to basically force this equation to be incompressible. Previously, we forced it to conserve mass by solving for density. But now we need a way to force it to be incompressible by enforcing this. And this equation is like du dx dv plus dv dy equals 0. We solve for u here, then what does solving for u do for us here? How do we figure out which is the correct u? We need to couple this directly into the equation, and as you can probably tell, that's pretty tricky. So how are we going to do this? So here's what we'll do. We will take the equation and just forget about pressure gradient for now. So density, whatever, gone. And we're going to be thinking about this part. Something we'll go over later, but this part is the sorry, let me think for a second. Should be the non-divergent part of the... So this is the non-rotational part of the fluid. I know it's Coriolis, you think of rotation, but if you take no, wait a minute. Let me check something. Non-divergent part. Yeah, so never mind. I guess we'll get to that later. Basically, we get rid of pressure gradient, so no pressure gradient. And we solve each of the equations for u star and v star. It's like an kind of intermediate variable for intermediate time step. And then we can just form this variable as like a vector variable with u star and v star in it. And then we can kind of solve this kind of artificial time derivative where we're dealing with this v star term. But to get to our final time step, because we're kind of in this in-between time step, we need to solve this equation. The next time step minus v star over your change in time. And that's equal to the pressure gradient, which we just ignored over here. And so we can solve this equation for this. So it's v star minus delta t times the pressure gradient force. We must have that the final velocity we get to, this is what we're solving for. By the way, this should be more like this. So I'm going to avoid confusion. The final thing we want to get to, this, it must be non-divergent. So we can actually plug this in to here, so we get this. We can put the divergence, apply the divergence through, and divergence of a gradient is a Laplacian. So this is what we have, and we can solve for the Laplacian part. So Laplacian of p is equal to rho over dt times the divergence of our intermediate value. And what we need to do is now solve this equation, solve it. We need to basically move this Laplacian to the other side and solve for the updated time step pressure. So now, by construction, the new pressure is corrected to allow the final velocity un plus 1 to satisfy the mass continuity equation. And by the way, this n plus 1 is basically equivalent to t plus delta t. So we start at a time t, and then t plus delta t would basically be the second time step, which we denote as n is the current time step, n plus 1 is the next time step, n plus 2 is the next time step. So great. Now, briefly, I just want to sort of go over a few things. How do we solve this equation? One way is you can kind of form a matrix equation system and try to solve it by basically inverting L. But that can have some issues. I think the more common way, but it's also kind of tricky to figure out how to do, is fast Fourier transform, or FFT. Basically, you apply FFT on both sides. Now you're in Fourier space, so you can use these like wave numbers, kx, ky, and basically solve these derivatives in Fourier space, which are these I, kx, I, ky, where I is a complex number. And you can basically divide on both sides this term, and we can solve for p hat, which is like Fourier space version of pressure, and then we need to use inverse fast Fourier transform to get it back into actual pressure. This algorithm is like a more complicated thing, which I won't go over, but that would be the kind of method that could be used to solve it. But also boundary conditions are also important for FFT, so that's important. But now that we have the corrected Pn plus 1, we can do our final step, which is to solve for the next time step, which will just be V star, and then you have the dt times the pressure gradient. That's coming from when we did this step here. Now we've corrected P, we do the exact same thing. We actually plug this P back into this equation. So that's what we have here. And yeah, again, just to show that that's 0, you can just show again. You take the divergence of both sides of this equation, you get the divergence of this is not equal to 0, but the divergence of this term is now equal to the convergence of U star, which is opposite of divergence, so they just subtract each other out and become 0. So yeah. So now that we know how to do it, I just want to go over where this comes from. So there's something called the Helmholtz-Hodge decomposition. Helmholtz is also the person, I believe, who came up with the theory for Kelvin-Helmholtz Instability in like fluid dynamics. So yeah, kind of famous name. I believe it's the same person. But the idea is any fluid velocity can be split into a part of the fluid velocity that is called solenoidal, which is the divergence-free part. We want in incompressible fluid, that would be the incompressible part. And we have a non-rotational part, which would be the kind of extra part that is associated with the which is associated with the compressibility, sort of. That's kind of a way to think of it. So we split it up and we say that the non-rotational part must be some gradient of a scalar. And because the curl of a scalar is always 0, so that's just, you can pick whatever you want is 0. This is the one that we know, so we'll just do that. And then this part is non-divergent, so we define it by saying that the divergence of U sol is 0. So if we then take the divergence of this equation, then this part will be 0, like we just said. And this part is defined as the Laplacian, right? So if we can solve the Laplacian of phi is equal to the divergence of u for phi, the scalar, then we know the scalar, then we can go back to this equation, which if you plug in this, you end up getting this. You plug the scalar in, and if you know U, then you can get U solenoidal. So you need to know U. Need to know U. Make that not a main comment, but just a like little comment. So in the projection method that we just learned, we basically solve this intermediate step called V starred. Let's just say that's what U is. We have this thing called V starred, which is a incompressible, or sorry, it's not really neither incompressible or compressible, but it's definitely not incompressible. So we can say, oh, this is a fluid. It has a non-divergent and non-rotational part. And then we can say, okay, what is the non-divergent part? That's the velocity that we want to solve for, because we want to have a incompressible fluid. An incompressible fluid, by definition, have this. Their divergence is 0, so that's what it is. And then the irrotational part, non-rotational part, that's just the pressure. That's not the pressure gradient, but it's the acceleration that the fluid feels, that part of the fluid feels from the pressure gradient. And if you remember, we did this. We solved this equation that's like un plus 1 minus u star over dt is equal to PGF, the pressure gradient force, which is this, PGF. And we also know that the scalar is just this inverse density times Pm plus 1, because we need to solve for the updated pressure. So if you go back to this method and re-look at these, you will see that this is literally the same exact thing as Helmholtz-Hodge decomposition. So I actually just found out about both of these methods today, which I've been kind of thinking about this problem for a long time, just kind of a curiosity of mine. I think I've asked like before, and I've been told about this thing called the Poisson pressure equation. And I think it's this equation. And so I'm always like, where's that coming from? Like, there's not really a proof of some equation for pressure like this. Well, this works for incompressible fluids. It comes out of using this method to couple the two equations, which are this equation and these equations. So in reality, if we're dealing with a compressible fluid, it's going to be, like I said earlier, to just use equation of state and thermodynamics, and you won't be able to do this kind of coupling. There's multiple problems in that case, because first of all, you can't get this kind of equation because rho is not constant and this term is still there. That's basically about it. So I hope that you learned something, and thanks for watching. And if you want, like and subscribe, and follow, keep watching for more videos. Yep. Thank you. Bye-bye.